Let's start with an introduction to Lisp. I am within my editor Emacs running the Emacs Lisp interpreter, the REPL. REPL stands for Read, Evaluate, Print Loop. What this program does is read the input I have, evaluate it, print it, and loop. That is, it lets me do that again. I typed in the numbers evaluate to themselves, and the printer also gives me another representations of this number as there is the octal representation, the hexadecimal representation, or the ASCII character representation. Other elements of the type system in Lisp would be, of course, floating point numbers. If I type them, I get them back, or strings. All of these types are also known as atoms. And atoms are things within the language that evaluate to themselves. They stand on their own. Another atom you have are symbols. Symbols are what you might encounter in other programming languages as variables or function names. They are the words you use to describe your language. For example, the symbol Emacs version holds the value of a string 28.1. That is my Emacs version. A symbol holds a value. When I evaluate the symbol, I get its value back. If you are used to other programming languages, you might be surprised that I use the dash to connect these two words into the same symbol. In many other programming languages, we use the underscore, or maybe we do this with camel case writing. But in Lisp, the dash is a legal character within a symbol. This is not interpreted as Emacs minus version because the way we describe function calls is in prefix notation, and the way we separate symbols is by spaces. So minus is a legal character in a symbol, as plus or slash or the $sign. All are legal characters. Before I show you how I use the minus sign, let me summarize you how we use function calls. In most languages, you use, the function name, the one you're going to use, and in parentheses, the arguments, first, second, third argument, and you separate them by commas. What you do in Lisp is to shift the parentheses to the left side, and you get rid of the commas. Now you know Lisp. This is the standard Lisp form. It's a list, actually, bounded by parentheses. But the way this is evaluated, interpreted is, as I open the parentheses, it means call the first element, which is the function, with all its arguments, which are space-separated symbols. What this looks like, I have, for example, the function upcase, and its first argument would be hello. I evaluate this into hello, all capitals. Let's go back to operations. For example, 5 minus 3. Well, in Lisp, the minus would be a function, and we follow our prefix notation. So we put the function as the first element of the list, and then what follows are their arguments. 5 minus 3 is 2. Another nice thing about Lisp is if you learn math, you generally learn or must learn about precedence rules. That means that the multiplication has a higher precedence than subtraction. And that this would mean, you first multiply 5 times 3, that's 15, and then you subtract those 15 from 9. In Lisp, learning the precedence rules disappears because you have to define every function call within their parentheses, and the parentheses give you the order of evaluation. And you go from the innermost parentheses to the outermost parentheses to evaluate the value. As we'd expect, 5 times 3 is 15, and 9 minus 15 is minus 6. The last thing I want to show you is that in Lisp, we can work with the symbols themselves. This is what gives Lisp a lot of its power, is the homoiconicity. That is that code and data are honestly indistinguishable. They are the same. As I showed you before, Emacs version evaluates to its value, but if I quote the symbol, it evaluates to the symbol itself. The same way I can quote an expression, for example, 5, 6a, and this evaluates to that form, which is a list. If, for example, is a special form. It's a special form because it changes the rules of evaluation. We don't evaluate all its arguments first before calling into the function, as we would have done here, evaluating the inner expression and then the outer expression. And if we evaluate the condition, for example, is 4 bigger than 0, if that is true, we return yes, otherwise we return no. Evaluated this, of course, gives us yes. If I change the order of that expression, now I say it's 4 less than 0, well, no. Working on the REPL is nice, it's interesting, but it's not the way we work. The way we work is within our editor in a buffer, and the nice thing of working with Emacs is that the evaluator is also integrated into the editor. If I, for example, type the expression 5 plus 8, I can directly evaluate this expression in line and see what the result is, given by that arrow. And I can keep maybe nesting my expressions, the multiplication of 5 plus 8, that times 2, that evaluates to 26, that holds also for example I showed you before. And this is really a nice way to interactively work on your code. I can say join of hello world separator like this. I'm going to join the list of strings to hello world all capital letters. Now this might annoy you. It still annoys me. It means that you always have to read your code twice, from left to right, as you maybe are used to it from your way of reading. And that is my first pass to build context. But then I read from the inside to the outside, a second pass, to understand the data flow. I start with the list hello world. I will join the elements of the list with a string with a separator empty space. And then I will uppercase that string to see hello world, which is what I expected. Lisp gets its name from list processor. Thus, the last thing I want to show you is how you manipulate lists. Let's first start with the empty list. That will be quote, open, close parenthesis. And as you see, it evaluates to nil. Nil and empty list in Emacs Lisp are the same. And nil is also the only false value. For example, if I have this inequality and it evaluates to false, it evaluates to nil. And when I had my if statements, so anything I put here that is not the nil and even integer 0, it still evaluates to true. Only nil is false. The way we construct lists in Lisp is, of course, as I have showed you before. And when I evaluate that, it evaluates to the list itself. The basic unit of a list is the cons cell. Cons cells are composed of two elements, the car and the cutter. Those are ancient names. The car is the contents of the address part of the register, and the cutter is the contents of the decrement part of the register. You just need to think it's the first and the rest of the list. My first cons cell, if I make the console 5, 8, and I evaluate this, you see it's 5.8. That is how you represent that the last part, the cons, the cutter is a value. However, were I to put here nil, you see this is a list of only one element, the 5. And the way we build list is we keep consing one console to the next. You see I'm consing the 9 to another console which has the 8, and that points to the console with the 5, and that points to the nil, to the nowhere. And that's how you build lists. That's essentially what a list is. And there are special type of lists. for example, an association list. That is a list where each element is again another list or a console. Here I would say 5A, 8 is B. You can think of this as what you're used to in JavaScript as an object, or in Python as a dictionary, is a key value pair. We call them association lists because they keep the struct. They are made out of lists. Searching in these lists is linear time, not constant time as you would expect from a hash map. But for small things, they are fast enough. And there are functions to look in them. For example, the ask. If I want ask of 5, it will look for the console that starts with a 5 and give me that cell. So I get 5.a. I look for the 8 one, I get the 8.b. I look for a 9, I get nil. It couldn't find that one. Let's talk about equality relations. The first equality symbol function we have is eq. And this compares if two objects are the same. And it works for numbers. So 5 is equal to 5. 5 is not equal to 9. It works for symbols. So the symbol A is equal to the symbol A, but not to the symbol capital B. Works for things that evaluate to themselves. However, that would be my first exception. The string A is not EQ to the string A because they instantiate in two different places in memory. And at that moment, I have to use different equality operator, equal. It compares actually the components of the object themselves. And this is something to keep in mind, that you have different equality operators depending on what you're comparing. Why is this important? In association lists, ask compares using EQ the requested value to the first element of the console, the key. For example, when looking for the symbol B, I get the console BB. If I search for 5, I don't find it. When I want to look for the value component of the cell, in this case the string A, I have another function, rask. However, as I explained before, strings do not compare equally with EQ. Thus, rask of the string A results in nil. But rasoc compares with equal, so I then do find the first cell A.A. Now it is convenient usually to get the elements of a list. For example, in the console 5.8, the first element is the car, that gives me the 5, and the cutter gives me the 8. In the same way, if I have on my search, I want the car of the solution, I get the symbol A. I want the color of this solution, I get the string capital A back. And that's it. That's all the Lisp manipulation you probably are going to do on Lisp.